Hi all, welcome to new class. Today's class is about extrinsic semiconductors. So in the previous class we have discussed about intrinsic semiconductors. Next is extrinsic semiconductors. So a semiconductor in an impure form is known as extrinsic semiconductors. Next we have to know about doping. The conductivity of silicon and germanium. So silicon and germanium are examples of semiconductors, and the conductivity of this silicon and germanium can be increased by the controlled addition of impurities to the intrinsic semiconductor material, and this action is called doping. So, doping means addition of impurities to the intrinsic semiconductor in order to increase the conductivity of the semiconductor materials. And a doped semiconductor is called extrinsic semiconductor. When an intrinsic semiconductor is doped with a pentavalent atom, so there are pentavalent and trivalent atoms. So when an intrinsic semiconductor is doped with pentavalent atom, it is called donor doping. And when it is doped with trivalent atom, it is called acceptor doping. And the extrinsic semiconductors are of two types. They are N-type semiconductor and P-type semiconductor. So the extrinsic semiconductors are of two types, N-type and P-type. N-type means negative. The short form of negative is N-type. P means the short form of positive, that is P-type semiconductor. And N-type means to increase the number of conduction band electrons in the intrinsic silicon, pentavalent impurity atoms are added. Then we get N-type semiconductors, and if we add the trivalent impurity atoms, then we get P-type semiconductors. So N-type semiconductor is obtained by adding pentavalent impurities. So pentavalent impurities means the examples are arsenic, then phosphorus, then bismuth and antimony. So these are the atoms with 5 valence electrons. So pentavalent means the outermost shell has 5 valence electrons, and the examples are arsenic, phosphorus, bismuth and antimony. When these atoms are added to the intrinsic semiconductors like silicon and germanium, then we get N-type semiconductors. Let us take the pentavalent impurity antimony Sb. So its outermost shell has 5 valence electrons, that is there are 5 valence electrons, and the silicon has 4 valence electrons, and only 4 of the 5 valence electrons of this, so there are one more electron here, so only 4 of the 5 valence electrons of the impurity atom, that is the antimony atom, form covalent bond with neighboring silicon atoms. That is, the silicon has 4 valence electrons. That is, so one will be here. That is, so in this way it will make bonding. That is, this is the electron in the outermost shell of antimony and this is the electron in the outermost shell of silicon. So here also let us draw. Silicon has 4 valence electrons. So one will be here. Here also. So in this way it will be making covalent bond with the neighboring silicon atoms. And this 5th electron does not have an atom with which it can enter into a covalent bond and therefore it becomes a free electron. So this will be a free electron. And thus every impurity atom donates one free electron to the silicon crystal and hence a large number of free electrons are available which make the crystal conducting. So the impurity atoms are called donor atoms. So these are called donor atoms. And here most of the current carriers are electrons. Silicon doped with pentavalent atoms is N-type semiconductor. That is N for negative charge of the electron. And the electrons are called majority carriers. Majority carriers. So electrons are called the majority carriers in N-type materials. And out of these majority carriers there are also a few holes that are created when electron hole pairs are thermally generated, and these holes are not produced by the addition of the pentavalent impurity atoms. And the holes in N-type materials are called minority carriers. So the holes are produced due to the electron hole pairs and these are called minority carriers in N-type semiconductors. Next is P-type semiconductor. And here, to increase the number of holes in intrinsic silicon, trivalent impurities like boron, then indium and gallium are added. So we will get a P-type semiconductor. P for positive. And let us draw the diagram. Let us take boron. So this boron has 3 valence electron in the outermost shell. So that is called trivalent impurity. And silicon has 4 valence electrons. So here each trivalent atom forms covalent bond with the 4 adjacent silicon atoms. And all 3 of the boron atoms are used in the covalent bonds. That is, the silicon has 4 valence electrons. So it will form like this. Here also 1, 2, then 3, then here and here this silicon has 4 valence electrons. So one will be in covalent bond with this boron, but here 4 electrons are required, but a hole result when each trivalent atom added. So here one vacancy of electron is there, so that is called hole. So let us make these electrons like this. So these are electrons. So the vacancy of electrons is called hole. So there will be a hole here. The trivalent atom can take an electron. It is often referred to as an acceptor atom. So here the trivalent atom can take an electron, so called acceptor atom. So here a hole is created due to the addition of this trivalent impurity, and this trivalent atom can take an electron, so it is called acceptor atom. And here most of the current carriers are holes. So silicon doped with trivalent atom is called p-type semiconductor, and the holes are called majority carriers in p-type semiconductors. Although the majority current carriers are holes, there are also few electrons that are created when electron hole pairs are thermally generated, and these free electrons are called minority carriers. Minority carriers. And these are not produced by the addition of the trivalent impurities, only due to the electron hole pairs. So that is about the extrinsic semiconductors. Hope you understand the extrinsic semiconductors, that is both the n-type and p-type semiconductors. So thank you for watching the class. If you like the classes, please like, share and subscribe my channel.